Hi, my name is Jason, and this video is the first in a three-part series explaining the stack from Nand2Tetris. In these videos, I will explain arithmetic and logical commands. While I will be mentioning memory access commands where they show up, I won't be covering them in depth. In this first video, I will cover the stack machine abstraction. In the second video, I will compare the abstraction to the implementation. In the third video, I will talk in more depth about the implementation. In this video, I will walk through the two examples of the stack machine from the lecture to provide some intuition about how the stack machine works. Specifically, I will be looking at the arithmetic commands example from slide 39 of the lecture, which I have here on the left, and the logical commands example from slide 40 of the lecture, which I have here on the right. In order to explain these examples, I will be comparing the stack machine to a deck of cards, just like the deck of cards which I have in my hand. I like to think of the stack machine as a deck of cards because a deck of cards literally is a stack of a group of objects. Also, with the deck of cards, I can easily take a few cards, I can spread them out, and I can merge them back together into a small pile. And this will be very useful for visualizing what happens in the stack. I'm going to now walk through the arithmetic commands example. If you can't see the printout that I have in front of me here, I would recommend that you find the original slideshow on the Nand2Tetris website so that you can follow along with my demonstration. I'll have a link to that in the description of the video. In this example, we are trying to solve for the expression d is equal to parentheses 2 minus x parentheses plus parentheses y plus 9 parentheses. We have the variables x, which is equal to 7, and y, which is equal to 12, and these are somewhere in our RAM, but we don't know where they are in our RAM. But for this example, that's not important information. We also can see that we have an empty stack, and that SP, or stack pointer, is pointing to the first available spot in our stack. I'm going to hold off on explaining what stack pointer is until my third video on the stack machine implementation, because I think it'll make a lot more sense then. But you should know that SP, or stack pointer, is going to be popping up throughout the different parts of this example, but I'm just going to ignore it for now. I also wanted to mention that the stack is also somewhere in our RAM. We don't know where it is yet, but know that's in the same RAM, just the same way that our variables x and y are, but they're going to be in different parts of our RAM. And so here on the right, I have my representation of the variables x and y. I like to represent variables as a bunch of index cards, where I have a pile of 7s because x is equal to 7, and I have a pile of y's because a pile of 12s because y is equal to 12. We also have d here, which will become important at the end of the example, but it's not relevant right now. Okay, so the first step in this demonstration is to push 2 onto the stack. Or since we have an empty stack, just push down 2. So I'm going to take this index card with 2 written on it to represent the value of 2 in memory. And so I'm just going to put that down, and this is going to be the first card in our stack. I'm going to move this so I make sure I have enough room to go downwards later. And this 2 that I have right here corresponds to the 2 in this rectangle at the in this part of the diagram. Our next step is to push x onto the stack. So I'm going to take one of these 7s next to x and put that down on the stack. And so there's 2 things I should mention right here. The first is that I always have this card, the lower card, overlapping. So for example, 7 is overlapping on 2 a little bit, and I do this to show that 7 is the top of our stack, even though we're moving in the downwards direction. The 7 is still at the top and the 2 is at the bottom of your stack. I also wanted to mention variables, is that we could pretend that this is an infinite stack of 7s, and every time I push x, I just take another 7 off the stack. In reality, I don't have an infinite number of cards here, but since this is programming, we can think of it kind of like at a high-level language. Every time in a high-level language we use a variable, we don't run out of it. We can just keep using the same variable x or y or whatever as many times as we want to. It's the same thing in the stack, where I could just keep taking cards off this pile to use as many values or as many copies of x as I needed to. Okay, so our next step is to subtract 7 from 2. And so this is how I like to think about it. This isn't 100% accurate, but I like to think that I'm going to use this subtract card, which I kind of just made up, and I'm going to merge these 3 cards together. So 7, the 2, and the subtract card, I'm going to merge together. I'm going to flip this over and have the output of 7 minus 2 on this card. Because this -5 comes from 7 minus 2, and then we take all of those cards together, we merge them, and we treat this card as if it's a single thing. We treat this card as if it's a single card. And to make that super clear, I'm just going to staple this together so it can't go in and like dig up the old cards. So here is our new card, -5, which corresponds to this part of our diagram. And this is kind of how I like to think about where the 2 and the 7 disappear to, because we see here that we have a 2 and a 7, and they disappear, and we're left with a -5. So this is just how I like to visualize it. Moving on to our next step in the example, we have push y. So just in the same way that I pushed x, I'm just going to take a copy of y and put that on the top of our stack. Our next step is to push 9 onto the stack, so I'm going to take an index card with 9 written on it and push that onto the stack. And our next step is to add the top 2 values in our stack. And so since -5 is at the bottom of our stack and 9 is at the top of our stack, so our top 2 values are going to be 9 and 12. So I'm going to use an add card to represent the addition of these 2 numbers. And I'm going to take these cards and, quote unquote, if you use your imagination with me, merge these together and create this new card, which is going to be 21, because 9 plus 12 is equal to 21. And then we treat this new group of cards, we treat it as if it were a single merged card, just as we did with this -5, as in I can't go back and dig up the old cards that are underneath it. We just treat this as if it's a single new thing. And to make that super clear, I'm just going to staple this one. So now we have a -5 and a 12, which corresponds to this part of the diagram in the example. Our next step, it corresponds to this part of our diagram right there. Our next step is to add these to the 2 top values in our stack together. And since we only have 2 values in our stack, by definition, these are the only values that we can add together. And since we're treating both of these groups of cards, this group of cards and these group of cards, as a single thing each, we just add them up the same way how we added previously. So I'm going to use another add card, merge these together, flip over this add card with the result. And so -5 plus 21 is equal to 16. And that is how we get the 16 right here in our example. And then one last time, I'm going to staple all of these together because we treat this big group of cards, again, as a single thing. Alright, so that is how we get to 16. And our very last operation here is to pop this value, or pop the top value in our stack, over to D. And so since we only have one value, this is by definition the top of the stack. And so I'm going to pop this over to D. And this is the same thing as assigning D this value. And then in the future, if we wanted to, we could pop D onto our stack, which would mean putting copies of 16 onto our stack. And so now right here we have all of our variables set, and this matches up with the end of the example. We have x equal to 7, y is equal to 12, and d is equal to 16, where d is somewhere in our RAM, but we don't know where it is. Alright, so that wraps up this example, and I will be looking at the logical commands next. Alright, so now we're looking at the second example for logical commands, and in this example we are trying to solve the expression parentheses x less than 7 parentheses or parentheses y equal to 8 parentheses. And to start, we can see that in our memory, or in our RAM, we have 2 variables, x, which is equal to 15, and y, which is equal to 8. We have an empty stack, and of course we have stack pointer, but I'm not going to mention that until my third video. And then here in front of me I have my representation of the variables x and y, which I'm representing with index cards. Alright, so our first operation here is to push x onto the stack. So I'm going to take a copy of x and push that onto the stack, and so this is going to be our first value in our stack. Our next operation is to push 7 onto the stack, so I'm going to take a card with 7 written on it, push that down, and now this 7 is the top of our stack. Our next operation is to check if the first value in our stack is less than the second value in our stack. Or I should rephrase it. I should say that we were trying to check if the top value in our stack is less than the next value in our stack. So I'm going to represent this operation using this card with LT for less than written on it. And I'm just like with subtract or add, I'm going to merge all of these together, or pile them all together, and flip this over with the output of that operation, which is going to be false. And in this course, 0 is false. And I'm going to pretend that this group of cards that I just made a pile out of is a single thing. So to make that super clear, I'm going to staple this. And so now we are at this point in the example with this false, this 0 corresponding to this false. Our next step is to push y onto the stack, so I'm going to take a copy of y and push that on top of the false, or the 0. Our next step is to push 8 onto the stack, so I'm going to take an index card with 8 written on it, push that down on top. And our next step is to check if the top 2 values in our stack are equal to each other. And so our top 2 values here are the 2 8s, because of course the 0 is at the bottom of the stack, this 8 is in the middle, and this 8 is at the top, even though we're moving down in the downwards direction. And I'm going to represent this operation with the card with EQ written on it. So I'm going to take these 2 8s, slide them into a pile, and flip over this EQ with the result of that operation on it. And since 8 is equal to 8, the output of this operation is going to be true, which in this course is -1. And we're going to treat this group of cards as if it were a single card. So I'm going to staple these together. And now we have our false, which is 0, and our true, which is -1. And our last step of this example is to check the top 2 values with a OR operation. And so I'm going to represent this with a card with OR written on it, and our top 2 values are our only 2 values in the stack, which are false and true. So I'm just going to merge these. I'm going to treat both of these groups of cards as if they were a single card each and just merge them or pile them on top of each other like I did before. I'm going to come in with the OR operation, flip this over with what I already know is the output of this operation, which is going to be true, and that's -1, and I'm going to treat this new group of cards as if it were a single thing, so I'm going to staple these together. And now we're left with the true or -1, and that corresponds to this part of our diagram. And that concludes my demonstration of this example. I forgot to mention this while recording the video, so I'm now recording this on my laptop. In the 2 examples that I explained, you may have noticed that all of the commands which we performed using the stack machine, such as add, subtract, less than, or equals to, are all things that we could already do in assembly language. So a few questions you might have are, why do we use a stack machine at all? Or why do we solve expressions in this incredibly complicated way? Or what does the stack machine bring to the table? The answer is that the stack machine allows us to implement loops and subroutine calling, which we'll see in Chapter 8. To put it simply, the stack machine allows us to create complex functions that we couldn't do in assembly language. Chapter 7 is all about setting up the foundation for Chapter 8, but Chapter 8 is where the stack machine becomes useful. That's everything I want to say in this video. In my next video, I'll be looking at the program and data flow in the VM emulator.